Dear students, today we'll discuss what is called as a transport phenomena in kinetic theory of gases. Yesterday, we have discussed about mean free path and the introduction about transport phenomena in kinetic theory of gases. Transport phenomena are characterized by the transport of, say, momentum, energy and mass of molecules under non-equilibrium condition or unsteady state of the gas. This phenomena is explained when the gas is in unsteady state or non-equilibrium condition. When the gas system or a gas is in non-equilibrium condition, gas tries to bring or comes to the equilibrium condition. During the non-equilibrium condition to equilibrium condition, a process of a transport phenomena takes place. So when gas is under non-equilibrium condition, the gas transfers its momentum to different regions. As a result, gas molecules, they move in a different direction when it is in a random state or in a thermal agitation. It has a different velocity. So the different molecules have the same mass but a different velocity. So the momentum, mass into velocity, is transferred from one layer to the other layer. Similarly, we have a thermal agitation. Gas molecules, they have the energy, and that energy is nothing but heat energy. When gas molecules or a gas itself is in unsteady state or a non-equilibrium condition, the molecules which are having a higher temperature, molecules or a region or a layer which is having higher temperature and the layer which is having lower temperature, molecules of the gas which is at higher temperature will have the higher energy, will have the more energy, and that energy will be transferred to the region where the temperature is low. There is a transportation or transfer of energy known as a transportation of energy, and that leads to thermal conductivity. Here I have written transport of momentum. When transport of momentum takes place, that results into the viscosity. Similarly, when there is a transportation of energy, when the gas is in unsteady state or non-equilibrium condition, the molecules at higher temperature will have the more energy, and the energy with molecules which have the more energy, they will transfer or impart that energy to the region where the molecules have the lower temperature, and therefore there is a transfer of energy, and that leads to a concept or phenomenon called as thermal conductivity. When a gas is in unsteady state, the distribution of gas molecules is different. So gas molecules, they will move from higher concentration region to the lower concentration region, and that results into the diffusion. Viscosity, thermal conductivity and diffusion is due to the transportation of momentum, energy and mass. And this is what is called as transportation of momentum or transport of momentum leads or gives rise to viscosity. transportation of energy gives rise to thermal conductivity, and transportation of mass or a transfer of mass gives rise to diffusion. Here we are discussing this transport phenomena one by one. In our syllabus they have mentioned the expression for coefficient of viscosity, and it is denoted by a Greek letter eta. Well, I have drawn here a figure already. Let me explain the expression for coefficient of viscosity or transportation of momentum. Here, transportation of momentum or transport of momentum. Fine. We know gas is having the different layers, right? And when the gas is under thermal agitation or in an unsteady state, the gas molecules, they have the different velocities. They are moving with the different velocities. Fine. So the molecules, they have the different, say, are divided into different layers. I'll explain this. So molecules which are moving with in a layer with a faster velocity will transfer the momentum to the layer which is a layer in which the molecules are moving with a slower velocity. One layer which is moving with a faster velocity, another layer which is moving with a lower velocity. Molecules which are moving with a faster velocity will transfer the momentum to the molecules which are moving with a slower velocity or a speed. To explain what is called as transport of momentum, or to derive an expression for the coefficient of viscosity, I have drawn here the figure. Imagine the gas system has been divided into different layers. So here I have O, the origin. OX is a horizontal layer along which, say, the molecules which are in contact with this assumed to be at rest. There may be a container, maybe a pipe here. As we go up, I have drawn here the z-axis. Okay, so along the OX, the molecules are at rest. Assume they are at rest, and the molecules which are moving in the upward direction or along this z direction, they are gradually having the different velocity. As we move away from the O, the velocity goes on decreasing. Here I have taken a layer AB at a certain distance z from O, and in this layer that is shown here, in this layer the molecules, they have the drift velocity V. Let V be the drift velocity of the molecules in this layer. All the molecules, please remember, all the molecules, they move with the same velocity in this layer, that is AB. Now the AB layer is at a distance z from the origin O. So there is what is called as velocity gradient, dV by dz. As we move along this z direction or z axis here, normally we write it as y, here I have written it is z. As we move from this OX, the gas molecules here assumed to be moving from left to right. Okay, and as we move upward, the velocity gradually increases with the distance, and this dV by dz is known as velocity gradient. We have seen this as a temperature gradient, velocity gradient. This is velocity gradient. The velocity of the gas molecules along the x-axis assumed to be 0, and as it moves away from one layer to other layer, velocity goes on increasing with distance here, and this is known as velocity gradient. Keep in mind, this is velocity gradient. Let me consider one more layer above the layer AB as EF, and this layer is at a distance lambda, the mean free path. I will consider another layer CD below the layer AB, which is also at a distance lambda. We take this layer above AB and below AB, the layers EF and CD are at a distance lambda, because during this distance no other molecules will not be colliding with each other, and that's what the mean free path lambda is. It is the average distance between any two successive collision, and it's a straight line path. We assume that this distance is lambda, this distance is lambda. Now the velocity of the gas molecule at layer or in the layer EF is given by this V plus dV by dz into lambda. That is velocity of the molecules in the layer V plus dV by dz into lambda. Similarly, the velocity of the molecules in the layer CD is V minus dV by dz into lambda from the layer AB. We have taken this as V, the drift velocity in the layer AB. What happens? We have studied this viscosity concept. The molecules which are moving in the layer and moving faster with this velocity, this is faster velocity, this is slower velocity. This molecule or molecules in this layer, they impart the momentum to the layer which are moving in the slower moving layer here. The molecules, they say gains the momentum in this layer, whereas this layer loses the momentum. Let us start deriving this relation. Velocity of the gas in the layer EF, that is EF here, is V plus dV by dz into lambda. Similarly, the velocity of the gas molecule in the layer CD is V minus dV by dz into lambda. Now, we know that this is, say, three-dimensional space, say this is x-axis, this is negative x-axis, y, negative y, say z, positive, and the negative z-axis. Okay. So, if you consider that the molecules are moving in all possible directions, so we divide here, we assume that the molecules are moving from left to right along OX, fine. So here, molecules, they move, how many molecules they move in one particular direction? 1/6 of the total number of molecules, either they will move along positive x-axis or along positive z-axis or along positive y-axis or a negative axis, anyone. 1/6 of the total number of molecules, they can move along any one axis here. Once we get this, let n be the total number of molecules per unit volume. N, small n, be the total number of molecules per unit volume. Let m be the mass of each molecule. Mass of each molecule here, and say C is the mean or average velocity of the gas molecule at a given temperature. These are assumed data here. N, the number of molecules per unit volume. M, the mass of each molecule. C, the average velocity of the gas molecule at a given temperature. Now, the number of molecules moving, the number of molecules, say molecules in the layer, they are moving with velocity v plus dv by dz. Well, there exists a relative velocity. Different layers of non-equilibrium gas may have different velocities, results in a relative velocity. That means this layer or the molecules in this layer, they are moving faster relative to the velocity in the layer AB. The molecules in the layer AB, they are moving faster relative to the molecules in the layer C and D. There exists relative velocity of the different layers with respect to one another. So let us have this. Once we have this, the number of molecules moving from the layer EF to CD, the number of molecules passing from layer EF to CD per unit area of layer AB in 1 second. Hope you got this. Number of molecules passing from upper layer above the reference layer AB here, the number of molecules passing from layer EF to the bottom layer CD per unit area of layer AB in 1 second are equal to NC by 6. N are the number of molecules, C is the average velocity. 1/6 molecules, they move along any one axis or direction out of total. Now, once the molecules, they move from EF to CD, the forward momentum imparted to layer CD, that is forward momentum, say lost by this layer, forward momentum lost by layer EF to CD is equal to, I have written here, M the mass of each molecule, NC by 6 are the number of molecules which are moving from layer EF to CD into this velocity V plus dV by dz into lambda. This will have the dimension of velocity itself. Okay, lambda is the distance now. So V plus dV. So here the number of molecules, okay, that passing from EF to CD, we have written here, that is the forward momentum lost per unit area per second by the layer EF is given by this. Similarly, the number of molecules passing upward from CD to EF through this layer AB, that is number of molecules passing from CD to EF per unit area of layer AB in 1 second, that is NC by 6, the number of molecules they are passing. Now what is the forward momentum? What is the forward momentum which the molecule gains? The forward momentum gained by the molecules which are moving from CD, right, to EF per unit area of layer AB in 1 second, that is equal to, same as this, NC by 6. These are the number of molecules they move from CD to EF. M the mass of each molecule. NC by 6 are the number of molecules they move from CD to EF. in 1 second passing the unit area of layer AB, that is into V minus dV by dz into lambda. That is the forward momentum gained by the layer EF from layer CD. So that is CD to EF, and the forward momentum gained by this is this. Now, if you calculate the total or the net momentum lost by this layer EF per unit area of layer AB per second, that will be equal to, that is addition of this plus this, that is mnc by 6 is common. I have added this V plus dV by dz into lambda minus this. So if you simplify this, it will be equal to 1/3 mnc lambda dV by dz. So this is the net momentum lost by layer EF per unit area per second. Similarly, the net momentum gained by the layer CD while passing the molecules from CD to EF will be same as this. Same as this. Now, this is net momentum gained or the net momentum lost here from net momentum lost by the layer EF. That means because this layer is moving with faster relative velocity with respect to AB or with respect to each other, and this will gain the momentum with respect to this. The net momentum lost or gained by these two layers is given by this expression. Now, there exists a relative velocity. So, we will calculate what is called as the forward dragging force. Now here the layer CD gains some amount of momentum, hence the above layer EF, say above AB, tends to accelerate the molecules in the layer CD. In other words, the molecules in layer CD tends to de-accelerate the molecules in the layer EF. The molecules in the layer EF accelerate the molecules in the layer CD, whereas the molecules in the layer CD tries to de-accelerate the molecules in the layer EF. Therefore, there is backward dragging force per unit area, and this backward dragging force per unit area is equal to gain or loss of momentum per unit or per second, per unit area per second of this layer. And here we got this, that is 1/3 mnc lambda dV by dz. So the backward dragging force, because one layer accelerates the molecules in the other, in other words, the lower layer will de-accelerate the molecules in the upper layer. So there is a dragging force, and we define viscosity based on this dragging force. So the backward dragging force per unit area per second will be equal to gain or loss of momentum per unit area per second. That is, F is equal to 1/3 mnc by 6 lambda dV by dz. That is this. According to definition of viscosity, we have here the viscous force, that is backward dragging force, is a coefficient eta into what is called as velocity gradient, and that the backward tracking force is given by this, that is, say here F is equal to eta into dV by dz. If I equate this with this one, I get this equation eta dV by dz is equal to 1/3 n c lambda dV by dz. So this gets cancelled. So eta is equal to 1/3 n c lambda. Eta is the coefficient of viscosity, and the expression for the coefficient of viscosity is given by this equation. Here mass is, m is the mass of the molecule, n are the total number of molecules, that gives us the density of the gas. Once we know the density of the gas, eta is equal to 1/3 rho c lambda, and this is the expression for, say, coefficient of viscosity. Hope you understood this. If not, let me explain it in a few minutes once again. So, while studying the transportation of momentum, we know that the gas molecules are divided, or assumed to be divided into different layers. So, layers in which the molecules are placed or they move with different velocities. Molecules which are moving with a faster velocity in one layer, and the molecules they move in other layer with a slower velocity. There exists what is called as relative motion between the different layers, and that has been explained here in the diagram. We assume that OX and OZ and the gas molecules, they move from left to right. The molecules which are in contact with this x-axis, they have assumed that the velocity 0. As we move from the origin, the velocity goes on increasing, say uniformly with the distance, and this gives the velocity gradient. Let me consider a layer AB, and all the molecules in this layer, they move with this drift velocity v. Let me consider two layers, one above the layer AB, one below the layer AB. Layer EF is at a distance lambda from layer AB. Layer CD, which is below the layer AB, is at a distance lambda. We have taken the distance between these two layers is equal to lambda, because when the molecule is moving from layer AB to EF, or AB to CD, or CD to AB, AB to EF, they will not collide with each other. So the molecules which are in the layer EF, they move with this velocity v plus dV by dz into lambda, where dV by dz is velocity gradient, lambda is the mean free path. It is given here. Similarly for this layer, all the molecules, they move with different velocities in a different direction. So we have possible 6 directions. Out of total number of molecules, if you consider the molecules which are moving along a particular direction, they will be 1/6. Fine. N are the total number of molecules per unit volume. M is the mass of the molecule. C is the average velocity at a given temperature. Let me consider the number of molecules passing from the layer EF. This layer is a faster moving layer. EF molecules, they move from EF to CD per unit area of the layer AB in 1 second, and the number of molecules passing from EF to CD per unit area of AB in 1 second are Nc by 6. So the forward momentum lost by the layer EF by transferring the molecules from EF to CD, the forward momentum is nothing but mass into velocity. This gives the mass, these are the number of molecules and the velocity. The number of molecules they move from CD to EF is again Nc by 6. The forward momentum gained by the molecules when they move from CD to EF through the layer AB is given by this. The net momentum lost by the molecules in the layer EF per unit area per second is given by this expression. Similarly, the net momentum gained by the molecules in the layer CD, if you add, you will get the same expression which I have not written here. As I mentioned here, there will be a relative motion between the layers, and that results into a dragging force, and that backward dragging force per unit area per second is equal to net momentum gain or lost per unit area per second is given by this. And this backward dragging force by definition is nothing but the viscosity, what is called as viscous force. What is called as viscous force among the layers of the gas system here. And that n eta dV by dz is equal to this, that results into expression for coefficient of viscosity. Now how does this coefficient of viscosity varies with temperature? Effect of temperature on the coefficient of viscosity. We know as the density decreases with increase in temperature, density of the gas decreases with increase in temperature, whereas as the temperature increases, the mean free path increases. If you take the product here, rho into lambda, it remains constant. Therefore, we know the average velocity is directly proportional to square root of temperature. Therefore, eta is also directly proportional to square root of temperature. Similarly, effect of pressure on the coefficient of viscosity. Here the coefficient of viscosity is independent of variation of pressure. Independent of variation of pressure. Here eta is independent of pressure because the density of the gas increases with pressure and the mean free path decreases with the same proportion or same ratio. Therefore, this rho into lambda remains constant, and therefore eta, the coefficient of viscosity, is independent of pressure. So we need this. So I think I have cleared all the points. We'll